Welcome to your first lecture of the Physics 105 course. And we're starting with probably the same thing that half of your science classes up till now have started with. I think it's really standard to start by talking about this. So we're not going to spend a ton of time on it, but that doesn't mean it isn't crucial. So I don't want you to take the fact that we don't talk about this for very long to indicate that it's not very important, but we're talking about measurements. We're going to talk about the SI system. We're going to talk about scientific notation and all of that because it's really important and it's something you really need to have a solid grasp on to succeed in this class. But again, we're not going to spend a ton of time because I'm assuming you've done it before. I always like to start off talking about this by thinking about how carefully do we really need to measure things? Because I think that's something that doesn't always get covered when we think about all this range of things that we can measure, is how carefully do we really need to measure? So we're going to start off with two stories that are perhaps a little bit about careful measuring. So in the 2008 Olympic Games, Michael Phelps was really kind of star of the games, the swimmer, the U.S. swimmer, and he won the 100-meter butterfly to earn his 7th Olympic gold medal of that competition. He beat Milorad Kovic of Serbia by 0.01 seconds. 1/100th of a second as they were finishing the race. It actually looked like Kovic was going to win, and Michael Phelps took this kind of awkward looking half stroke and managed to just beat Kovic on the touch at the wall. There were pictures posted in Sports Illustrated detailing it. There was controversy. This win actually let Phelps tie the record for the most gold medals in a single Olympics. Mark Spitz, who had the record before, or who held the record up until that point, till Phelps actually won an 8th gold medal during this games, has sort of called into question whether or not Michael Phelps ever won this race, and there was controversy surrounding it. It was 1/100th of a second. It was also a new Olympic record. So that's an example where I think we would all say we need to measure really carefully. We need to time really carefully because that's so close. But what about this? In fall of 2011, a group of physicists who were part of the OPERA experiment, which was 160 physicists from 13 different countries studying neutrinos. And neutrinos are these neutral subatomic particles that are really fascinating. And part of what they were doing in their study was they were shooting neutrinos from CERN over here in Switzerland through a tunnel 732 kilometers, which is 454 miles, to another laboratory in Italy. And one of the things they were trying to do was measure how fast these neutrinos were moving. And one day they looked at the data and they found that the neutrinos had arrived after this 732 kilometers or 454 miles, 60.7 nanoseconds. So nano is 10 to the negative ninth. So 60.7 nanoseconds faster than they should have arrived if they were traveling at the speed of light. The scientists immediately started double checking their measurements because, you may or may not know, Einstein's theory of special relativity, which is a lot of what we base modern physics on, is partially based on the idea that nothing travels faster than the speed of light in a vacuum. And they had just measured, or possibly measured, something that did. And this was sort of referred to as the discovery that broke physics. So they actually tried to keep it quiet for a long time, and they started double checking everything. And then the data leaked. And they had to release their information. They actually released it in fall 2011, but the measurements had been made much, much earlier in the year. So on September 23rd, 2011, they held a press conference, and they said that they had an indication that neutrinos had traveled faster than light, and they kind of hedged their bets. They said, maybe, we're trying to validate it, we don't really know. But the news exploded. It was in the New York Times, it was everywhere that they had discovered neutrinos moving faster than the speed of light. Another group of physicists kind of came on board, they modified the experiment, and they tried it again, and they got the same result. And there's a lot of excitement, but a lot of kind of wariness because nobody's really sure. So then they decided they could test one more thing where they were, and they could compare the timing system on their apparatus to the timing system of another experiment. And they found an error in the timing system, a fiber optic cable that essentially delayed the start of the timer by something close to 70 nanoseconds. And they publicly acknowledged that their data had been wrong, and it was a huge uproar. The sort of head of the experiment, actually two of the heads of the experiment, the project leader and the experimental coordinator both resigned after a vote of no confidence. It was actually a failed vote of no confidence. But I bring this up, one, because it was a really exciting news story a few years ago, and two, because I thought we were measuring really carefully with the Olympics and swimming with 1/100th of a second. But this is a time when you need to measure within 60 nanoseconds. You need to measure better than that, and an error of less than 61 nanoseconds was front page news. So now that we know that we have to measure very, very carefully for some things and perhaps less carefully for others, we need to think about how we decide what a measurement is. And to measure any quantity, you have to have a standard. There has to be some reference. And I think a lot of people don't realize there are actual physical references for all of what we do. For example, for the kilogram, there is a cylinder of platinum and iridium that sits in a French vault. That is the standard kilogram. There are 40 replicas that are in countries around the world, and they actually weigh them against each other from time to time. And one of the issues they've encountered is trying to keep them clean enough so that their weights stay the same or their masses stay the same. For the meter, we've actually changed through time a lot what we have as the standard unit of the meter. It used to be 1/10,000,000th of the length of the meridian through Paris from the pole to the equator. And then the meter was defined as the length of this very specific platinum iridium rod. Now it's actually based on the speed of light and is the distance traveled by light in a vacuum at a very small increment of time. I'm not going to say the increment of time because unfortunately it's not an easy to state increment, but that's how it's defined now. For a second, it's actually now defined based on decay of the cesium-133 atom. So for each of these, we have a standard, and a unit, a kilogram, has the value of exactly one standard. So a kilogram is exactly the mass of that standard kilogram. From this one standard, we need to be able to express measurements across a really wide range. So if we think about length, we need to be able to express length for things like the size of the swine flu virus, which is on the order of 80 to 120 nanometers, up to the height of LeBron James, which is about 2 meters, up to the diameter of Jupiter, which is about 140 megameters. Obviously, we actually need to do things much smaller and much bigger than these, but they start to give you a sense of the sheer range that we have to be able to express with just this one really basic unit of measurement. So, how do we do that? Well, there are two very common methods for expressing very large and very small quantities. The first is just scientific notation. We express numbers using powers of 10. The second is using prefixes for units, and we have a table of prefixes there on the side. Some of these are likely very familiar to you, like kilo, centi, milli. Some, like zeta, are likely a lot less familiar, but they do all exist. If you ever need them in class, you will be given them as a reference. But just so you know, that's one of the standard ways of sort of expressing across this incredibly wide range of values that we have to express. So for example, 1 gigagram expressed using the prefixes is equal to 1 times 10 to the 9th grams expressed in scientific notation. In this class, we will use the International System of Units, Again, probably like every other science class you've taken, it's also known as the SI system or the metric system. And these standard units for length, time, and mass are all listed below along with their unit symbols. Basically, everything else we use, with a few exceptions when we get to electricity, is a derived unit based on these basic units. Now, if we were always given the data we had or the information for a problem we wanted in the units we needed at the end in meters and kilograms and seconds, it would be really quite fabulous. But unfortunately, that's not the way the world works. And we wind up needing to convert units a lot. Sometimes it's just that we understand the results better. I'll admit, I've been in science for a lot of years. I use meters and second all the time. But when I think about speeds for running or walking or driving a car, I really think in miles per hour. So I convert between meters per second and miles per hour a lot so I can get that sense. The same thing with heights. I think better in feet and inches for heights of people than I do in meters. And when we convert units, all we really do is multiply by 1. We create a conversion factor that is just a version of 1. For example, if 100 centimeters equals 1 meter, which it does, just in case anyone was wondering, then 100 centimeters divided by 1 meter equals 1. We can multiply by 1 forever and ever and ever and not change the actual value of our number. And that's all we do when we convert units, is we multiply by a lot of different versions of the number 1. As we do this, we also cancel units. When you work problems, you should always, 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 always keep track of your units. Keeping track of units can, 1, help you make sure your answer at the end is in the units they've asked for. It can sometimes help you figure out if what you've calculated is actually what you want. If you calculate something that comes out in meters per second and you were supposed to give an answer of length, well, that's not right, because length is just going to be in meters. And so it's really important. It's really easy to forget, I know, but it's incredibly important to do that. Part of keeping track of those units, again, involves canceling units. So when a unit is divided by itself, the unit disappears. You've already seen this some, so likely you know if you had the volume of a cylinder or something like that, like we see here on the side. If you take the volume of a cylinder and you divide by the area of one of the ends, you're left with the height. So we start off with volume in meters cubed or length cubed and divide by an area, which would be length squared, in this case meters squared. And we do meters to the third divided by meters to the second. We're left with just the units of meters, and that's an appropriate unit of length to be the unit for the height. So that's all for measurement, and you will hear from me again soon as we sort of start on motion in one dimension.